Hello, everyone, and good evening. Today, I'm going to talk about this paper. It's SCPOR Algorithm. It's an elastic workflow scheduling algorithm for service computing. So, what is an elastic workflow? Because the scientific process is too complex, computing and storage resources in scientific workflow are sometimes needed on an uneven basis. So the need of resources is elastically changing during the runtime of a workflow. Most of the workflow schedule algorithm that we already have, they only consider a computing environment in which the number of compute resources is bounded. That means resources assigned to a workflow cannot be automatically determined on demand of the size of the workflow, and they are not released back to the environment until the execution of the workflow completes. The salient feature of service-oriented computing have brought a new opportunity to schedule workflows on resources with elastically changing demand, as they allow resources to scale on demand as usage changes through dynamic provisioning. As you can see in the left figure, only one compute resource is required at the stage T1 and also T4, but at the same time 6 resources are needed for stage T2 and 4 resources are needed for stage T3, and this is for maximizing the task parallelism. In the right figure, the size of data consumed by each computing varies during stage T1 to T4. The input data could either distribute across 6 compute resources at T2 to maximize parallel computing, or partially centralize into 3 compute resources to minimize the data communication for the next step of task computation at level T3. A service-oriented computing environment, or SOC environment, provides scientific workflow with salient features that are distinctive from other computing environments. Compute resources in service-oriented computing environment are exposed as service to allow the access over the network. The other feature is the number and type of compute resources assigned to a workflow can be determined by service requests. And the number of resources assigned to a workflow can be dynamically changed at runtime. That means additional resources can be assigned because of the under-provisioning, and also unnecessary resources can be released back to the environment because of over-provisioning. And last but not least, not all requested compute resources need to be assigned at the beginning of a workflow execution. Resources can be assigned only when they are needed. To run a workflow in an SOC environment, as you can see in this picture, a user firstly makes a request to a workflow scheduling service, or shortly WSS. The request includes the type of compute resources for an execution of the workflow and the idle time threshold to release a long idle resource back to the environment. The WSS forwards the user request to a computing environment service, or CES, which is provided by the service-oriented computing environment. CES checks if the requested resource types can be provided from the system, and then returns OK if the type can be provided. After that, WSS will schedule the workflow for the SOC environment. So it is assumed that each task of the workflow can be processed on any assigned resources. And also an estimate of the task execution time on a resource is known prior to workflow scheduling. The computation of tasks on each resource can be overlapped with data communication between resources. Tasks assigned to one resource can be executed in parallel with tasks on other resources, but no task is allowed to run in parallel on two resources at the same time. So CES then returns a schedule result to the user. The user includes the number of a workflow resources and the cost estimation. If the user agreed to this schedule and requests to run the workflow, now workflow schedule service requests workflow resources from the service-oriented computing environment on demand of the need of computation and data storage. Once the resources are available, the workflow can start to run. So in this paper, there's three main parts that they talk about. First is formalizing workflow scheduling problem. Another section is scheduling algorithms. They presented the proposed two scheduling algorithm. One is task prioritizing algorithm, and the other is SCPOR that we're going to talk about. And at the end, in the experiments and discussion section, we compared the SCPOR algorithm with already existing scheduling algorithms. So in formalizing workflow scheduling problem section, we are not going to talk much about the formalizing, how they formalize it, because they only did it because to make it easier to run algorithm on. But there are some features that need to be explained. One is SOC environment, or service-oriented computing environment. It's an environment or a platform that provides resources and communication. A scientific workflow is a computerized model of a scientific process which consists of a set of tasks and a set of data dependencies between these tasks. Each task in a workflow is atomic. That means the operation of a task are not allowed to be interrupted during the task execution. A scientific workflow graph, as its name explains, it's a graph for scientific workflow. In the formalizing section, it has two extra components comparing to scientific workflow formalizing, and one is the nodes and the other is vertices. Earliest ready time, or ERT, is the earliest time when all predecessors have completed their execution and all input data have arrived at the specific resource. EFT is the earliest finish time of a predecessor of a specific task on a specific resource. And workflow makespan is the total completion time of a workflow. The scheduling algorithm section, this paper presented two algorithms. One is task prioritizing algorithm, which it ranked the order of tasks for workflow execution. The other is SCPOR algorithm. This algorithm is proposed to schedule workflows on an SOC environment. Actually, the SCPOR algorithm is an extension of the CPOP algorithm, which was applied for mapping a workflow application to a bounded number of processors. In task prioritizing phase, the task prioritizing algorithm is to order each task of workflow by its priority rank. and form a list of prioritized tasks denoted as list priority. Firstly, we calculate the average communication cost and computation cost for each task in the given workflow graph. After that, the priority rank for each task is calculated, and then we create a temporary list called list candidates to have tasks that are ready to be prioritized. The entry task is initially contained in the list, which means that the task is the first one to be processed. Since the entry task has no predecessors and its priority value is so far the highest in the list candidate, the entry task is removed from list candidates and added into list priority. Then successors of the entry task are put into list candidates. From task in list candidates, we select a task with the highest priority rank. We remove it from list candidates and then add it into list priority. In the next step, for each successors of the newly removed task, if all its predecessors are in list priority, which means that all the predecessors have already been processed, then the task is eligible to be selected into list candidates. Such a procedure is repeated until list candidates is empty, and in that case, all tasks in this workflow are ranked in list priority. Here you can see the task prioritizing algorithm pseudocode. In the resource selection phase of SCPOR algorithm, tasks are scheduled according to their priority in list priority. To minimize the workflow make span in SCPOR algorithm is to map all tasks on the critical path of the workflow graph to dedicated resource, so that the data communication costs between tasks on the critical path are eliminated. Well, first of all, we need to introduce the concept of the critical path as follows. Critical path, or shortly CP, in a given workflow graph like G, there exists at least one path from T entry or entry task to exit task, such that T entry goes to TI to TJ and all the way to T exit. The priority rank of each task in a specific set of tasks is equal to priority rank of the entry task in the graph. So if priority rank of a task is equal to priority of the entry task, then that task is critical task of the workflow. A set of critical tasks is known as list CP. A workflow may have multiple critical paths, and the SCPOR algorithm chooses one of them and select critical tasks on this path into list CP. So the first step of the SCPOR algorithm is to select a dedicated resource RC for execution of all critical tasks in the critical path. The total computation cost of critical tasks is calculated for each resource, and a resource that produces the minimum cost is selected as RC. RC is exclusively used for critical tasks until all of them are scheduled. And here is the algorithm, the pseudocode for the list CP, how we create list CP. In the SCPOR algorithm, the scheduling decision to task is based on 4 cases. One is if a task TI is a critical task. That case TI is mapped onto the resource RC, and the set of task resource earliest start time and earliest finish time is added into list schedule, and the available time of the resource is reset to earliest finish time of that task. If Ti is not a critical task and the resource Rs is available by earliest ready time of Ti, then Ti is mapped to Rs. The set of task resource EST and EFT is added into list schedule. Now, if Ti is not a critical task and resource Rs is not available at the earliest ready time of task Ti, in that case, a new resource Rn will be considered to be assigned to the workflow. And if Ti is not a critical task and the earliest finish time on any of new resources is later than minimum EFT, Ti is mapped to Rs, and the set of task resource earliest start time and earliest finish time is added into list schedule. And the available time of the resource is reset to minimum EFT. After each task assignment, a resource Rk that has been kept idle longer than the given threshold will be released from the assigned resource R. In this case, the number of workflow resources can be elastically scaled in. There are three reasons that might cause this situation. One is the initial assigned resource are more than sufficient for the workflow execution. This is basically over provisioning. The computing capability of resource is far less than any other assigned resource. This is also under provisioning. And an unbalanced workflow graph leads to an uneven resource usage. For example, a large number of resources are only recorded at the beginning of the execution. So we're going to show how a SCPOR algorithm actually works. So in this example, it's a workflow that is generated by a workflow generator. There are three resources, R1, R2, and R3, which is assigned to the workflow at the beginning of the workflow. And the list priority is already been created by the task prioritizing algorithm. And the list CP, which is the list of critical path tasks, is created by the list CP algorithm. So the three resources is assigned at the beginning of the workflow, which is R1, R2, and R3. The R3 is firstly assigned to T1, which is the entry task. So T1 is a entry task. That means it's a critical task and it's in the critical path. And all the critical and R3 is identified as RC, which is resource for critical tasks, which is the only compute resource released until the last critical task T4 is complete. That means RT, T1, T5, T11, and T13, and T14, all of them assigned to R3. And R3 are not going to use to another task until the end of the workflow. After T1 completes, T5 and T7 are scheduled on R3 as they are critical tasks as well. R1 is assigned to T7 and R2 is assigned to T6. And now the next task is going to be processed is T2, But because there is no resource available but the earliest start time of T2, so the workflow provides the SOC environment provides the workflow with a new resource R4. So T2 is assigned to R4, and also T4 is assigned to R5, and T3 is assigned to R6. Now, the next the next task is going to be processed is T8, which is assigned to earliest resource is going to be released, which is T2, and so on, T10 to R2, T9 to R5, and finally T12 to R4. As you can see, no task is going to be assigned to R3 because R3 is only dedicated to critical tasks. The vertical task, the horizontal dashed lines that you can see is the idle time of that resource. And here is the pseudocode of the SCPOR algorithm. In experiment and discussion section, we compare two algorithms, which is one is SCPOR and the other is SCPOP algorithm. The SCPOR and SCPOP algorithm are applied to a schedule that are randomly generated workflow with our random workflow generator. 3 compute resources are initially requested by the workflow, and tasks in the workflow are prioritized using the proposed task prioritizing algorithm. So, as you can see, actually the horizontal dashed lines indicates the idle time of each resource, and the vertical lines, these orange vertical lines are indicates the workflow make span scheduled by each algorithm. The results scheduled by SCPOR and SCPOP are shown in this two Gantt chart. The top one is SCPOP algorithm and the bottom one is SCPOR algorithm. The workflow make span schedule by SCPOR is 68.75, which is 33, which had 36.66% improved from the make span scheduled by SCPOP. The number of workflow resources start from R1 at the beginning, at the end, and it increases to 6 resources at the maximum, and then gradually drops to again 1 resource until the last critical task completes. The resource usage scheduled by SCPOP and SCPOR are 325.62 and 227.99 respectively. So the resource usage by SCPOR algorithm is 30% less than the SCPOP algorithm. To investigate the overall performance for computing-intensive workflow and data-intensive workflow, the developer workflow generator randomly generates 50,000 workflow graphs for each experiment. The communication and computation costs of these workflows are also randomly generated within the defined reasonable range. For each workflow, a compute-intensive workflow is considered when the total number of computation cost is at least 50 times greater than the communication cost, and data-intensive workflow is considered when the total number of communication cost is at least 50 times larger than the computation cost. Then we compare workflow scheduling result by SCPOR and SCPOP given various scales of workflow. The total number that one algorithm outperforms another is counted, divided by the total number of experiments. is considered as the probability of one algorithm outperforms another. As you can see in these two charts, in the top one, all 50,000 scheduled results scheduled by SCPOR outperforms the results scheduled by CPOP at each range of workflow size. And at the bottom, the probability that SCPOR outperforms CPOP continuously increased from 82.3% to 1 as the number of tasks from the range of 2 to 50 all the way to 201 to 250. That was all. Thank you very much for listening, and good day.